Alright, hello, I'm Ed, and today we are here to talk about hydroelectric power and tidal barriers. Hydroelectric power is produced as water passes through a dam and into a river. The more water that passes through a dam, the more energy is produced. Once a dam is built, an artificial man-made lake is basically created behind it. Electricity is produced by a device called a turbine. The turbine contains metal coils surrounded by magnets. When the magnets spin over the metal coils, electricity is produced. Turbines are located inside the dams, so basically the water will then flow inside it and turn these turbines, turn the magnets, and then electricity is converted. There are many pros and cons of having dams. Dams, they provide clean, pollution-free energy, but they can also harm the environment. Species that use rivers to spawn in are often hurt by dams. In northwest of America, sockeye salmon and trout populations have dropped from 16 million to 2.5 million since hydroelectric plants were built on the Columbia River. Dams all around the world have hurt many species. They're also very expensive to build, to design, and to manufacture. Systems won't work efficiently also if the water source has dried up or if there's not a lot of water flowing through the dam. So, for example, due to like dry winters or summers, things like that. If tide is not very strong as well, the magnets won't get turned as or the turbine won't turn as fast. So the magnets basically won't induce a high voltage or current. So you won't get a lot of power out of that, which is not great. Anyway, and basically these are the energy conversions in when using hydroelectric power dams. So it starts off with kinetic energy in the water, where the water flows from the river, whatever, into the dam. Then into gravitational potential energy, when the water then flows downwards, so the GP is increased. Then this then gets transferred into kinetic energy, as in the water is now moving really fast downwards and into the dam. And then the kinetic energy will then get transferred into electrical energy when it turns the turbines. The turbines then go around the magnets and the voltage or current is induced. And then it basically just goes through specific bits and basically gets transferred into electrical energy. And then back to kinetic energy again as the water then flows out of the dam and carries on through its little way. Anyway, now we're going to talk about tidal barriers. So you're thinking, what is a tidal barrier? A tidal barrier is a dam-like structure used to capture the energy from masses of water moving in and out of a bay or a river. So you're thinking, that's kind of similar to a dam. What's the difference between them? Well, instead of damming the water on one side like a conventional dam, a tidal barrage first allows water to flow into the bay or the river, and then it will release the water back during the low tide. This is done by measuring the tidal flow and controlling the sluice gates at key times of the tidal cycle, and turbines are then placed at these sluices to capture the energy as the water flows in and out. Tidal barrage power schemes have high capital costs and very low running costs. So this is basically good and bad with tidal barriers. Tidal barrier A tidal power scheme may not produce returns for many years, and investors may be reluctant to participate in the projects. But in the long run, they they're good. You make money off them basically. Okay, so you're thinking how what kind of ways can you obtain energy from a tidal barrage? Okay, well, there's the ebb generation of electricity. The basin is basically filled through the sluices until high tide. Then the sluice gates are closed. At this stage, they may be pumping to raise the level of the water further. The turbine gates are closed until the sea level falls to create sufficient head across the barrage, and then they are open so the turbines generate until the heat is again low. The head is again low, sorry. Then the sluices are opened turbines are disconnected, and the basin is filled again. The cycle kind of repeats itself many times. Ebb generation, it can also be known as outflow generation. It takes its name because the generation of electricity is known as the tide changes tidal direction. Then there's the flood generation of electricity. Basin is basically filled through turbines which generate at tide flood. This is generally much less efficient as ebb generation because the volume of the water containing the upper half of the basin is greater than the volume of the lower half. Rivers flowing into the basin may further reduce the energy potential instead of enhancing it as ebb generation, of course. This is not a problem with the lagoon model without river inflow. Then there's a thing called two-way tidal barrage scheme. Two-way electrical generation requires a more accurate control of the sluice gates, so keeping them closed until the differential head height is sufficient in either direction before being opened. As the tide ebbs and flows, seawater flows in and out of the tidal reservoir through the same gate system. This is of tidal water back and forth causes the turbine generators located within the tunnel to rotate in both directions, producing electricity. However, this two-way generation is generally less efficient than one-way or ebb generation, as the required head height is much smaller, which basically reduces the period over which the normal one-way generation might have otherwise occurred. Also, bidirectional turbine generators designed to operate in both directions are generally more expensive and less efficient than dedicated unidirectional tidal generators. Anyway, here are some calculations to kind of find out if hydroelectric power produces a lot of power. So the energy generated from a dam is calculated by using this equation, 0.5 times by the A, which is the horizontal area of the barrage basin, times by the P, which is the density of the water, which is a constant of 1025 kilograms per cubic meter, and times by the height, which is the vertical tidal height, and also that's squared, times by G, which is the acceleration. So we're basically, after performing all these calculations, which you can see here, I'm not going to go into them, but you can give you a bit of time to read them. We get that as the dam is 30% efficient, the power conversion is efficiency of 30%, so we get 511 megawatts of power produced. And then if we compare it to wind turbines, we use this equation K times by Cp times by a half P AV cubed, where P is the power output, Cp is just a power coefficient. It depends kind of the dimensions of the turbine. P is the air density, A is the rotor swept area, V is the wind speed, and K is just a constant 0.000133, which is just a constant to yield power in kilowatts. So if we basically take a normal day, where the wind is about 7 miles per hour, which is kind of average. We take a velocity, we kind of average velocity, then we take the density of air to be 1.225 kilograms per meter cubed, and the power coefficient to be around 0.3, which is kind of average, and the diameter of the wind turbine to be around 60 meters, so kind of an average size. We get there to be 11,307.12534 watts a day, which is kind of a lot less than you would expect, really, compared to other, like to the hydroelectric power. So overall, we've calculated that hydroelectric power produces more energy, but there are also many good and bad things though about wind power. And yeah, so wind basically, there's a lower cost per watt hour in a good location, which is good with wind energy. Smaller systems are used, so basically less maintenance, and there's a predictable power output in many locations. But the problem is it's not very suitable due to lack of resources. Towering can be expensive for large units. Some people don't really appreciate it's not very aesthetically pleasing. Birds of prey might run into it. The power output can be a bit sporadic, which is not great. Many people consider the noise to be quite high, and minor maintenance on a windmill can be difficult because it's quite a high, it's quite high up, and moving parts will eventually wear out. So many different aspects need to be taken into consideration when choosing between power outputs. Anyway, thanks for listening. This has been Edward Gabriele talking about wind power, tidal barriers, hydroelectric power. Thanks.